Hey everyone, this is our lesson on polarity, and by the end of this lesson, you should be able to compare the properties of ionic, covalent, metallic, and network solids. Again, we're going to focus a lot on covalent here, so you may want to stop and review your notes for covalent bonding, as well as electronegativity before we start, because that's going to play a big part in this set of notes. So first, let's make sure we can understand the difference between polar and nonpolar. So nonpolar means that electrons are shared equally. So there's an equal pull on both sides of electrons here. Your molecule, if you can draw it out and you can see a line of symmetry through your molecule, then that means it's going to be a nonpolar molecule. So just look at your VSEPR shape. Cl2 is a great example of this. It's identical atoms pulling on the same electrons, which means they're pulling with the same force, so they would have a nonpolar bond. And then a polar bond is where your electrons are not shared equally. The more electronegative atom in the compound will attract the electrons more strongly to their side. And you can also determine this if your molecule is asymmetrical. So if you draw it and there is not a line of symmetry because you have lone pairs in there, which really tend to throw it off, then you will have a polar bond or a polar molecule. Remember here, when we discuss polarity, like dissolves like. So that's another thing. If something dissolves in water, then it's going to be polar because water is extremely polar. So here are some examples of polarity. They've got a charged tube that they are putting near these samples. As you can tell, hexane is not bending towards that charged tube, which would be a nonpolar bond. Water is extremely polar because it's bending towards that charged tube. And then isopropanol does show some polar properties because it also bends towards the charged tube. So now let's add in with some electronegativities here. These are not really numbers to memorize. They're good to know. They're good to memorize. But I'm not going to test you on these numbers without giving them to you. So I could give you these differences and you would have to know if it's ionic, covalent, polar, that kind of stuff. But I don't expect you to just know these off the periodic table. But if your electronegativity difference, so if you take the two atoms that you're looking at, you subtract their electronegativity values. If it's between 0 and 0.4, then that is a nonpolar covalent bond or a pure covalent bond because it is equally shared. If the difference is between 0.41 and 1.69, it'll be a polar covalent bond. And if it is greater than or equal to 1.7, it is now an ionic bond. So that means we have got a metal and a nonmetal. Keep in mind a little caveat here with this section. You will see there are some metals which tend to be called soft metals, more so in the transition area part of the periodic table, where your difference calculated will fall in this polar covalent area. Based on properties, you can still say that they are ionic, so we don't tend to bring those up in terms of polarity difference, but just be aware there are some that give you the same values that fall on the higher end of this polar covalent, but it will include a metal. Oops. There is a good rule of thumb to follow, though, if you have your periodic table with you. So if elements are right beside each other on the periodic table, so they're not identical, but they're right beside each other, we can say this is nonpolar. It might not be as pure as, two identical atoms bound together, but it still will be nonpolar if they are right beside each other. So an example here would be nitrogen and oxygen. And then elements that are at least one away from each other or more on the periodic table will be polar. The further they are away, the more polar they get until it becomes ionic. So the distance on the periodic table increases polarity. So you can think here, nitrogen and fluorine, oxygen is in between those, they would have a polar bond. So how you show polarity on a molecule, if I tell you, like, show me the polar bonds on this molecule, so show me which side is positive, which side is slightly negative. You can use your deltas first. So if you do this little delta symbol, with a plus sign, that goes on your less electronegative element because that would be the slightly positive side, the one with the weaker hold on electrons. If you do delta minus, that's on the more electronegative element in the compound. Another way to do this is a hatched arrow. So the arrow itself points towards the more electronegative atom, but then you put a little hatch sign over the less electronegative atom that makes it almost look like a plus sign. So when you look at these pictures, I've shown you some of the forms to use the delta plus and delta minus. As you can tell, the slight positives are getting those delta signs. The slight negatives are getting the negative delta sign. And the reason we use these deltas is because these are not full charges. Remember that. We're looking at covalent compounds, so they're sharing electrons. One just is holding onto it tighter than the other. And then you also have this one here, which is the hatched arrow. So you can tell it points towards fluorine, which is the much more electronegative element than hydrogen. And over hydrogen, you put that little hatch mark, which makes it look like a plus sign. You can have a nonpolar molecule that does contain polar bonds. So just because it has polar bonds does not mean that it's going to be a polar molecule, because sometimes those bond polarities can cancel. Come on. You will have to look at the polar bonds, and they have to match these two conditions. So if they are on the same axis and they pull in the opposite direction, they cancel. So if you look here, we've got, and I'm going to draw this out so you can see the symmetry a little bit better. So if we draw out CH4, ooh, getting a little sloppy, sorry. We know that carbon is the more electronegative element of the two. So all of these are pointing inward. Well, if you look at the axes, so they are all pointing in opposite directions because they're all pointing towards the carbon. So if we first look at my y-axis, you can tell these two arrows are pointing in opposite directions and they're on the same axis. So these polarities will cancel each other. Then if you look on the x-axis, you will see that these two are also pointing in opposite directions and they're on the same axis, so they cancel. So this molecule itself would be nonpolar, even though it has polar bonds. So pause the video, draw that, so you can have that in your notes if you need it. So show the bond polarities in CO2. Is it polar? So I've got my picture right here, but let's go through the steps. You would draw your Lewis structure, so you see that here. Come on. You'll check the polarities of each bond off the central atom. So we've got that the central atom is less electronegative than the oxygen, so they're pointing both outward. Look at the molecular geometry or symmetry. Do the bonds cancel or not? And in this case, they absolutely do cancel. So the bonds are symmetrical and opposite. CO2 is nonpolar. So now I want you to try it with water. Remember, draw out the Lewis structure. Do not forget lone pairs if they are there, because lone pairs affect symmetry. So remember that.